Thank you, everybody. I'm director of the 1000 Immunomes project at Stanford and associate professor at the Buck Institute for Research on Aging. And my talk and focus today is about using space medicine to understand problems on the ground, but also develop countermeasures for risk associated with space flight. I founded the 1000 Immunomes project 15 years ago, and we have identified a metric for systemic chronic inflammation. We're creating interventions for inflammation, which is a lead cause of aging. I spun out a company out of stuff, and then 3 years ago, NASA reached out to me in the Human Research Program in Houston. Susanna Sanello told me, David, what you're doing in aging and inflammation is very well aligned with what we're studying here in astronauts. And I didn't really know about too much space biology, but this caught my attention. She was studying countermeasures for spaceflight related risks. And she passed away in December of last year, and I took that torch and I continued that type of research to do two things. One is create drugs for aging and longevity on the ground, and also countermeasures for spaceflight. I don't have to convince you that we have to reach the stars. Definitely a planetary surface is not the right place for an expanding technological civilization. And to get there, this poses a huge risk for human in space. And we've seen this in humans, we've seen this in animals that were sent to the International Space Station. But what you see in this graph or in this table is the risks associated with spaceflight and also the risk associated with aging. What happens is that during spaceflight, this happens at a much faster pace. So I would really like to argue that this is the first non-disease human model for accelerated aging. This is not terrible news, because when astronauts come back to Earth, there's geroprotective mechanisms that rejuvenate them. And so long-term consequences are not that bad, but they still have fibrosis, they still have cardiovascular aging, they have obviously some cognitive impairment that then gets recovered. So there's an opportunity. We are expanding now. The private sector is taking over, which is really great, because for the first time we have large-scale biological data from astronauts. We're working with SpaceX and Axiom to get all this data before, during, and after spaceflight. So we're collecting all this. We also have ground analogs. And we created a consortium for space health and human longevity. This is a non-for-profit to basically create a place where we could accelerate the research between these overlapping fields. I also created a company out of this, and the idea is that we leverage space medicine to enable expansion of the human race in time for longevity, but also in space. So this is the way our platform looks like. We do microgravity simulation. That's what we're taking into as a first step. And then we're going to do more radiation. For now, ISS is largely protected from radiation. We're now validating this in crew member data as well as in large aging databases. We generate compounds and we test those compounds at an accelerated fashion. The video is not coming up here. So we use human organoids. The reason is animals don't translate. And so we take these little organs from humans. These are immune organoids that you toss a flu vaccine that produce antibodies. They mimic very well what happens in aging. And we also use cardiac organoids and neural organoids. We do functional analysis, and we do all sorts of omics to understand the functional changes as well as the molecular signatures of these. So this is just data, a whole lot of data. In 24 hours of microgravity simulation, we can accelerate aging by 50% on these organoids. So we toss compounds and we see how they recover. In this case, I'm showing you accelerated inflammation, cellular senescence, altered mechanical properties. There's a remodeling of the actin cytoskeleton, and that seems to mimic very, very well what happens in fibrotic disease as well as in aging. The methylation clock is up in 24 hours of simulated microgravity. We create clocks. That's also what we do for a living. And in this case, I'm showing you the heart transcriptomic clock that when we put these organoids into the microgravity simulation, the aging of that clock gets accelerated, so another piece of data, and then we can identify or map this back to diseases of aging on the ground. In this case, what I'm showing you is both in our experiments as well as in public domain data sets from lamin mutation, which causes a type of cardiovascular condition. In both experiments, you see upregulated genes and downregulated genes that overlap at large. So we now have a model for cardiomyopathy, which solves a problem here on the ground. And when you do OMIM phenotype, which is a large database, we identify that our signatures of aging in this microgravity simulation mimic what happens in cardiomyopathy. We take all these genes and we build gene compound interaction analysis, and we are able to identify compounds that can reverse these signatures and improve the function. So all in all, we're developing drugs for both space-related risks as well as aging here on the ground. More on space data, so this is Inspiration4 data. We also have access to JAXA-6, and the European Union, we're contacting the European Space Agency. Yeah, and there's a very good correlation between space changes during space and what happens in our system. This plot on the far left represents the upregulated genes during microgravity. By large, this is immune dysfunction, inflammation, all of these things that we see on the ground during aging. So we test these compounds and we can reverse up to 70% of these differentially expressed genes in microgravity. We can reduce senescence, we can reduce inflammation. And what I think is happening here is that generally speaking, during aging, you have a remodeling of the extracellular matrix with degradation of elastin and deposit of collagen. So everything becomes stiffer, and the cell is sensing these mechanical forces. In space, that's quite the opposite. You're unloading the system, but the end result is exactly the same. So there is a fine threshold at which cells function in an appropriate way. Then if you go beyond or above that threshold, you get epigenetic reprogramming, you get mitochondrial dysfunction, cellular senescence, and overall aging-related features. So what we're trying to do here is to develop drugs for age-related dysfunction as well as space-related dysfunction. This is our founding team, and I'm happy to take questions here. Awesome. Yeah, Adam.
Bad news is, does anything get better in space?
I don't think so. I mean, based on what the data says, both bacteria and viruses become more virulent, and we have immune dysfunction, we have cardiovascular dysfunction. So that I think what we need to do is to really take this very seriously, because the space industry has been dominated by engineers, and that's all good. We need to build our rocket. But what happens at the molecular level in humans is not looking good. I think the reason is we have evolved in a very particular environment. You change any species that you put in a new environment will develop inflammation. That's in a nutshell. Yes, clearly.
I would, is the good news that you're giving us that space is in some sense an environment that produces accelerated aging in humans, so it can produce accelerated insights and treatments for aging, rather than tracking somebody for 30 years as they naturally age, or trying to compare old people to young people who are different people. Now you can have the same person. And so the upside of it, things get worse in space, is they get worse faster, so we can develop curatives and stuff faster, right?
That's right, we're pivoting exactly on that front, yeah.
Okay, wonderful. What is your challenge?
Yeah, I guess how we improve the infrastructure to develop clinical trials in space.
Wonderful, okay.
Yeah.
All right, thank you so much, David. This was wonderful.
Thank you much.